So good afternoon. My name is Herm. I'm a systems engineer for Aruba Networks, so they pay my bills. I work for Aruba for the last 4 years, so next week will be my anniversary. And I have a security background, and because of that, quite a lot of ClearPath experience. Before I joined Aruba, I worked 13 years in the field, so I have not only sales experience but also engineering experience. So for today, session about client roaming. So let's start about designing guidance on roaming. So something about the planning of your channels. How to place access points, and how radio resource management or adaptive radio management, how we call it in Aruba, will help to optimize roaming. We'll look at clients actually roaming. How do they make their roaming decisions? How can we facilitate them to improve the roaming? And I have some slides about troubleshooting. So if it doesn't work, where can we start to find out why it doesn't work? Short, shameless plug, Airways community, you should all be familiar with that. The larger version of this slide deck with all the Aruba specific things are available on Airheads, and they are in the VRD, the Validated Reference Designs guide. So you can get the full presentations and lots of other presentations, for example, about building very high density networks, which will not be covered today. It's also there. So one thing to take into account when talking about roaming is that the channel, the air channel where the client is, it's like a hub. So one can be speaking, and all the others can hear it. So like the old coax Ethernet and the old hubs, that's how Wi-Fi works. And that means that when we talk, and we have two tables of people talking, they will hear each other, and they can't communicate at the same time. So what can we do in Wi-Fi? Because we have on 2.4 multiple channels, so we have 3 of them. We can put on different channels, and that allows us to speak on both tables at the same time. If we have multiple floors in the building, we'll need to. It will be more complicated. So we have channel overlap, the well-known co-channel interference, and we must take that into account and make sure that there is the least amount of co-channel interference, so it will not hurt the two meetings, and they can all talk. So. What channels do we have in 2.4? We have, of course, 1, 6, and 11, and depending on who you're asking and who you're talking to, they will tell you there are 4 channels in Europe. So you can use 1, 5, 9, 13. It depends on your environment if that will work. But as told before, 2.4, it's a disaster area. So we should have a look at the 5 gigahertz as well. There we have more channels. So we have 20 megahertz channels. We can have 4 non-DFS channels in the 5 gigahertz band. So the lower 4, and in the US they have 5 more channels in the upper part of the band. We don't have them in Europe. And in addition, we have 15 DFS channels, so that makes it a total of 19 that we can use for channel selection on 5 gigahertz. If we go to the double bandwidth, so to the 40 megahertz channels, we only have two channels available for 40 gigahertz non-DFS, and we have another 7 with DFS. And for the 80 gigahertz, we only have 1 non-DFS channel and 3 others that will do DFS. So one thing about the channel width. So our POC lab in Sunnyvale, they did quite some testing about high density, and they found out that if you are increasing your density, the total throughput with 20 megahertz channels is better than with 40 or 80 megabit channels. So what we see here is the 80 megabit channel. So you see with the number of clients increasing, you see rapidly decreasing the total channel capacity. If we do that with 40 megahertz channels, it improves. So with 100 clients, we still have about half the bandwidth. And with the 20 megahertz channels, we see it even improves a bit more. So not for the bidirectional, but for the uplink, it does. So when designing for high density, or when designing for roaming, we should decide, should we use these DFS channels? And if we do the calculations, if you have a few more access points than only 1 or 2, you typically will need to use those DFS channels in Europe. But we need to take into account how are we planning? So what are the expectations of the throughput? Do we really need to use 80 megahertz channels? Also, how far are the APs spread from each other to reduce the co-channel interference? Another thing is that many clients refuse to use certain channels. So yesterday, the site from Mike Cabano was mentioned. He has an overview. It's not very extensive, but at least for a few clients. You can see that if it will support the DFS channels and if it will allow you to use those. And I think it's good if this spreadsheet can be extended and that we have more data available on what client capabilities are. Another thing, if you do have DFS, do you have enough non-DFS coverage to fall back? So we've seen situations in hospitals where the automatic radio assignment put a very nice channel plan in place. But what it didn't take into account is that there were some US-based chipsets in that hospital, and there were coverage holes if you take out a part of the band. So they were experiencing client roaming issues, and that could be solved by putting in basic coverage on non-DFS channels and fill that up with DFS channels. If you don't want to do it on 5 gigahertz, is the 2.4 gigahertz spectrum, is it clean enough to fall back if clients don't get on your 5 gigahertz network? Another thing to look for if for radar detection, are you close to an airport or to a seaway or to a weather station. So we've seen reflections from weather stations in large buildings, and there it was the other way around, where a university reflected through a large building, and the weather station was seeing clouds where there were no clouds. So it took quite some time to find that, but if you are close to those radar-using institutes, make sure that you at least very thoroughly monitor the channels and if radar events are detected. Yeah. So the question is, will the standard Aruba adaptive radio management plan, so you have the basic coverage on DFS channels and extended coverage on non-DFS, so you have also always a basic DFS coverage? The answer to that is currently no. So at this moment, that's not part of it. So that's a reason why you might put help our ARM to build that standard non-DFS coverage in your network, and let the other APs find out themselves what are the best DFS or non-DFS channels. Also, with DFS, I know some of you put static channels on 5 gigahertz. If you put a static channel, so don't have it automatically assigned, take into account that if you hit a radar event, the radio has no other choice than to shut down. If you can move to another channel, operations will continue, but if you have steadily set to a specific channel, it will not, the AP will not move to another channel. And also on 2.4 gigahertz, we don't have those radar issues. So, what channel width should we be using? If we're not using DFS on 80 megahertz, there's just one channel, so not really, really useful in these environments where we are. Probably in our home environment, if you still have one access point. But probably most of you have multiple access points at home, so probably there it will always be a problem. So 40 megahertz channels are problematic as well, as you have only 4 channels. Sorry, two channels available with 40 megahertz bandwidth. So you can have only few access points, and with 20 megahertz. We also have only 4 channels available, which are non-DFS. If we are using, in that case, we can have 4 80 megahertz channels in ETSI, 9 in 40 megahertz, and for 20 megahertz, you can have 19 separate channels on 5 gigahertz. And I think we can conclude from that that if we are in the European Union or in ETSI, we should probably use the DFS channels, with the remarks that some clients don't support it, and you should take into account that you have a basic coverage on the non-DFS channels. So another thing that affects roaming is the transmit power. So we can put access points on maximum power. You can reduce the power. With many adaptive radio management systems, you can automatically let the system decide what should be the power of the access point. And the Aruba system will work to a situation where you have the maximum coverage while you have the minimum co-channel interference. So it will end up in a quite stable situation where you have the best settings. For roaming, It's also important because if you put the access point on a as a very loud screamer, clients can hear the access point, but they might not have the power to get back to the access point. Let me see. Oh. So what we typically see is that the APs they have better receivers, and so they can listen better. But also the clients they have lower power, so they can't transmit at the same power as an access point can send. So for that reason, it looks or it seems better from practice. That you will set your power levels to a lower signal than the maximum power. Also for high density, you will probably need to lower the power so you have the more capacity and less co-channel interference. Few metrics for good data rates on 11N. You will need an SNR of approximately 25 rep, and for the 11 AC with the highest data rate, you will probably need a 35 SNR or better. As soon as SNR goes down, your speed will go down, and the amount of airtime used for transmitting the data will increase. So about the power levels, of course power levels are always related to the background noise. So you are designing for a signal to noise ratio, not necessarily for a specific power. Power levels can also be too high. So last week on Airheads, there was a posting which is some testing. If you have a too loud talking AP, it will effectively reduce the data rate. So powers can be too high. And radios will introduce internally noise and reduce the signal to noise ratio. So powers can be too high, and signal strengths of minus 50, minus 55 dBm. Those can be considered as being too loud. And it has some other drawbacks that we will cover later on. So another problem with roaming, or the reason why we want to have good roaming, is the down rating. So as soon as we see the signal strength or the SNR decreasing, the wireless client will and the AP will use a lower data rate. And the problem of the lower data rate is that it will take more airtime to push the data from A to B. So we want to prevent that downrating, and we can do that by improving the roaming. And because the radio is a hub, the increase in airtime for low-rate clients will affect all users on the same channel. So we're all sharing the same airtime. So if one client goes to the very low bit rates, it can bring down the total performance of the network. And we've seen quite overall throughput improvements just by making clients better roam, because they have higher rates and they can push much more data through the air in the same time. So what can we do to increase the roaming? From practice, we found out that one of the things you can do is just eliminate the lower data rates. So if clients or the access point or the network doesn't support 1 megabit or 2 megabit, clients are forced to roam to an access point nearby where they can get better data rates than the very low. And a setting that works in many cases is cutting all the data rates below the 11 megabits. And I have some examples of that in future slides. Sorry.
That would be a problem in this hotel, cutting the data rate below 11.
Yeah, because there is nothing above 11. Yeah, that's for sure. Yeah, we're not talking about this hotel. By the way, there are some devices that have issues with that. So in hospitals, medical devices that are working on ancient hardware, 11B, sometimes 11A, they can refuse to connect to the network if the lower data rates are not there. So you need to have some good testing before you cut out those data rates. So we have some example configuration. So you see here all the data rates below 11 are cut out. And another thing that will improve roaming is that the beacon rates, you can set it at the same 11, but we recommend to put it one level higher. So you can put it on 18 because that will limit the cell size of your access point. Clients need to be closer to your access point to hear the beacons and to pick that access point as a candidate to roam to. Again, extreme care is required in very critical environments like hospitals and medical. Then the placements of the access points. So you need to place the access point very well distributed, so you have a very equal signal strength over your building. And also, because cabling and putting access points to the ceiling, it's very important to have a good design. I don't think I should tell you, because you know, but a good design is really critical. If you're doing voice over the network, it does matter where the APs are mounted. Because mounting is very expensive, make sure that you do it right in the first place, and you have only one time to place those access points. So too many access points is not good. Too few access points is not good. So design is very key, and also for the adaptive radio management to make the right decisions, it's good to make the access point shielded from each other, so they shouldn't be all in one line, but yeah, more distributed, where you have some shades from the construction of your building. It can be walls, it can be the elevator shafts, so it can be anything. So distribute the access points where they can't hear each other. Also, if you have multiple floors, it shows out that putting the access point at the same location every floor is worse than that you stagger them over the different floors. Access points in the hallways, there are situations where you can't get out of that situation. If you can avoid it, Do avoid it because all access points in one line, it will cause huge numbers of code channel interference. Putting the access points in the rooms will putting the access points in the room will improve that behavior. So for roaming, when a client wants to roam, it's important that it doesn't see too many access points. If you see too many access points, because roaming is a client decision, the client will probably make a bad decision on which access point to roam to. And also putting the access points spread it across the rooms instead of in the hallways will improve that because clients will hear less access points at less signal strength. And if we are talking about the signal strength, I think there was a 10 dB number. Make sure there are just a limited number of access points within that 10 dB level from the maximum power, so the client can make a good decision for the alternate access point for the roaming. Then about AP density, some rough numbers. In warehouses, you typically place an access point every 750 to 1,000 square meter, where you have a 50% overlap, so that will be one access point about every 30 meters. For retail, you can go down to 30 meters interval of the access point. For the open space offices, you can use every 15-20 meters an access point, and if it's closed off space with rooms, you typically will need a even better design and walk around that building to make an estimation. So you will need more AP density if you have more users, or you have more devices per users, or if you're using an all wireless office. So we see few companies moving now to all wireless office. So wireless will be the primary connection medium. And sometimes there is a wired backup. Sometimes there isn't even. So it should work, and the design should be good. One thing about the internal antennas, we have quite some APs with built-in down-tilt antennas. If you put them higher, the circle around the AP or the cone coverage area will increase. So you can play with that as well. Then if we have a very dense deployment, we're talking about APs every 10 or 15 meters. And as we've seen in the figures in dense deployments, you typically will fall back to 20 megahertz channels. Adaptive radio management. That's the Aruba implementation of the automatic channel assignment. It works pretty well. So in most customer deployments, this is what we advise, and which is the standard, and which will turn on. It will automatically work to a situation with the maximum coverage and the minimal interference. For roaming, we might need to help adaptive radio management a bit, because adaptive radio management by default has a very wide number of power levels it can choose from. So it can go from I think 6 to 21, 23 dBm. And for the roaming, you want to have that more equalized. So you don't have very strong access points and very low power access points at other places. So the roaming will work best if you have an equal distribution of the power. So some guidance with an open system, you typically put the APs on 12 to 15 dBm, so it can choose between 12 and 15. So you have a 3 dB spread. If you put them closer, go to 9 to 12 or 6 to 9 for very close access points. On the 5 gigahertz, we have some more space, we have some more air, so we put the powers on the 5 gigahertz a bit louder. That has another benefit, because if clients can choose between a 2.4 gigahertz channel and a 5 gigahertz channel, if the 5 gigahertz channel has a lot of power, it's more likely to choose that channel, so you will get kind of automatic band steering to pull those clients to the 5 gigahertz band. By putting the power on the 5 gigahertz, a bit louder, and it can be a 6 dB plus for the 5 gigahertz band. That works quite well in practice. So for roaming, basically, the client will make the decision to roam. We can help the client by having the good design, by having the power levels well set, but in the end, as long as the clients don't support 11V for the steering from the network, the client will make the decision on where to go. It will primarily check at the power. So for that reason, make sure not that many access points are available at high power for a client to choose from. Some modern clients can use the 802.11k system for neighbor reporting and channel reporting, so it can make some more intelligent decisions, but we've seen not all clients will do that. So what happens if a client is connected to an access point and it starts moving? If it starts moving, we'll see the signal strength. It will go down over the time and the distance. And at a certain level, the access point, the client will see the signal is getting critical. I'll need to find another access point. It will send out probe requests, and all the access points in the neighborhood will respond to that probe request, so the client can choose from one of the access points. Again, the more access points that will respond to those probe requests, the more difficult for the client it is to make a good decision on which access point to choose from. So when the client moved, it chooses the right access point, and it has a better signal strength. So it will be okay. So what happens if we put the access point power too high? So then when we start walking, we still see enough power. So it will be very late if the client even responds to the access probes for new access points. It will be very late, and also there will probably be more access points responding. So it's very confusing for that client, and the client is likely to make not the best decision for itself and or for the network. So about 802.11k, 802.11v, it's 11v is a new standard. It's supported in iOS 8. It seems to be supported only on on the iPad and the iPhone. My Nexus 5 Android phone will do it as well, but I have an Nexus tablet, and that one doesn't. So I think it would be useful to have an overview about what clients can do 11v, what clients can't do. Part of that for concepts. So one of it is the 11K neighbor report. So the AP can tell the clients, I have these neighbors available for you, so it doesn't need to probe for access points that are in proximity. It just gets a table. You can select an access point from these available access points. This also can be used to steer clients to more preferred access points. So you can leave out specific access points where you don't want to have that client steer to. By the way, these are radios, not access points. The second one is the other way around. So the client can can tell to the access point or to the network, I can see these access points. If the network has that information, can combine it with its own topology and improve the information of where clients should go. And 11K can also tell which channels are used by the wireless LAN, which is important in DFS because many clients will not probe for DFS channels automatically. And then for the steering part, 11v, the BSS transition management, that allows the network to move a client to another AP. Again, very limited support in clients. It seems to be getting better because this allows us to control the clients from the network, which has also always been very problematic in Wi-Fi. And it seems that finally we can do that. So, a few things about Placementcement. The original slide deck, it's available on Arubapedia, has a lot of information of how to configure it on Aruba network equipment. I didn't want to bother you with that detail. In basic, what it does, from the network perspective, it will check what is the best radio where a client will be connected to. And it will gather information from the 11K reports about the signal to noise ratios. It will also check all kinds of other frames on signal strengths. So it will build a model of what will be the best distribution of clients over the network, and that can be that all clients must go to the 5 GHz band, or it can be in a crowded area that clients must be spread over multiple access points. It's some magic going on, and it will improve your network. One thing in bold, client match is not a roaming tool, so it will, in the end, force clients, if they are very sticky, taking up too much airtime, it will steer those clients. But it's always better that the client itself will do good roaming, so you still need the correct drivers for proper roaming over the network. But at the end, it can save your network from a few sticky clients that are taking up all the airtime. And it might do that even by disconnecting those networks. It also will keep track of clients that cannot be steered. So if clients refuse to steer or they fail to steer after a few times, they will be marked as unsteerable. So we will not try to steer clients anymore. One little trick about iOS is that if within a 300-second interval client is disconnected 5 times, iOS will mark that network as unavailable and will refuse to connect back to the network automatically. So the question is, when you talk about tier, is that always DAuth or can it be 11v? So yes, it will be 11v, unless the client doesn't support. So it's a staggered approach. We try to steer it nicely with 11v. If it's not possible, the network performance is at risk, and then we will DAuth or blacklist the client. What happens is it will be blacklisted for 10 seconds, so it will not see the access point, and then kind of roaming action will be initiated by the client. Yeah, so that's in the detailed slides. I left them out for today, but the client match, it is voice aware. So if a voice call is going on that client, it will not de-authenticate the client. So it's quite smart. There are a few other smart things. So with the new 11AC Phase 2, with the multi-user MIMO, multi-user MIMO only works if clients connected to the access point do support Phase 2 multi-user MIMO. So you can use client match to distribute legacy clients, AC Phase 1 clients and below on one access point, and pull the multi-user MIMO clients to another access point that is available. So some nice things. For you as engineers, this is all very nicely monitorable. So you can see what's the virtual beacon report of a client MAC address, and you can exactly see which SSIDs, which radios are seen at what signal strength. So we can see how the client has moved through the network, why it has moved, because it was band steering or it was a sticky client, all the reasoning. So it gives a lot of data about the moving of the client through.
Just a question for you on that last screen. Can you get this from the Aruba utility on a Android device? This screen? See.
Yes, you can, because there is an SSH client built in to the controller, and you can run this command on the Aruba utilities.
So you'll actually be able to sit someplace and see how you see the AP and how the AP sees you, and all of the K&B information. I mean, that means you go back one slide as well. So all of the information is in the VBR is also available from the client itself.
Yeah, it should know. Yeah, it should know its own VBR. Yeah, because it sends it itself. I'm not sure. I can have a look and.
I thought that's kind of meta that you see yourself seeing yourself, but from a troubleshooting standpoint, you could see a lot. I just wish that the utility ran on iOS, so you could actually see this, since the Androids don't support the other. But sorry.
No, absolutely. So we're still building, and I think this is good feedback, so we can improve the utilities. By the way, the Aruba utility is an Android tool which you can use to monitor your network connection. Gives all kinds of very deep, technically deep, detailed information. It also works on other networks, not just Aruba. Although with Aruba, it can log into the controller and fetch AP names and all kinds of information to make it a bit more. But it also will show you the roaming, so you see bars every second to which AP you are connected at which strengths. So if you're walking, you see the bar going down, and then you see a roam, another color. And so you can, from the client, exactly see what's happening on the network. So what can we what can we do if we want to have more information about the clients and their roaming? So we can have a look at the association, authentication, and the network connectivity. So what is important, is the user associated, is he on the network? What AP is he connected to? Does it make sense that the client is on that AP? And if we wait some time, does it move to a better AP if it's not? So that's a good start. To look. From the controller, you can see a show AP association client match, client MAC, sorry, which gives lots of information about that client, which AP is connected to, at what data rates, what are the signal levels, things like that. Also, it shows the association, so we can see the channel noise, which channel, how it's connected, how long it's connected, if it has been steered from client match. We can even see if the client is 8211V capable, so there's a capital V here, which is in the flags, and this is my Nexus 5 phone. I made a screenshot this morning on the IAP 205H. It's the same one that you will receive, so you can do this at home or in your lab. On that access point, you can perfectly see which clients are 11V capable and steerable. So it also works on the instant portfolio. For Windows, we can use the NetSH WLAN show interface command. So there we can see to what BSID are we connected, what's the authentication, which channel, what are the rates, although the signal and the rates on Windows seem to be a bit unreliable. The data that we get from the controller is much more accurate. On a MacBook, you can use the airport command to get similar information. For the association, we can get all kinds of information from the controller. This is from the controller again, about packets that are sent. The retransmits, the last receive SNR, so quite a lot of detailed information. And with the AP client trail info, you can see how the client moved through the network. So very useful. Did it pick all the access points that you wanted to have that client to go for? So for authentication, if we're doing we must take it into account that on a roam of the client, it will do a new authentication. That can be the full .1x authentication, which we don't want to have at every roam. To prevent that, we can use PMK caching or opportunistic key caching to reduce the full authentication to a very limited four-handshake re-authentication. But you must make sure if your client is roaming and is doing a full .1x authentication with TLS certificates, it can put quite some burden on your radio server. So make sure the radio server is good, the latency is good, it's responding well. On the other hand, we also still see a lot of problems with the drivers. So also with roaming problems, it can be a driver issue, and updating your driver may improve the performance of the client on the network. So PMK caching, OKC. So check your radius server. What are the response times, the time to live, and the round trip times for your radius server. And you can on the controller do a show auth trace buff, which will extensively tell you what's happening. So this is a complete .1x authentication. So you see the station up here doing many handshakes, and at the end the client is connected to the network and each success there. So this is the normal one. If we have a roaming event, so the client roams, here we see there is an issue because the client will do the full authentication on the roam. So probably OKC was not configured, or PMK was not configured, or something with the client, which can be true. If it works, if you have cached keys, you will see there is a very limited re-authentication. And again, the authentication also takes time. So if during a roaming you lose a lot of time with the authentication, for voice probably you will hear some hiccups in the voice. And this is an example of a client driver issue. So you can read that in the slides on the network. Other things, make sure your DHCP server is running okay. So some clients, when they move from one AP to another, they will renew the DHCP reservation or their lease. So make sure the DHCP server is responding quickly and is capable of doing the amount of work. This is how it looks. So we got through the design, the channel planning for roaming. So make sure you have at least a basic non-DFS planning for your clients available, and you can fill that up with DFS channels on 5 GHz on the 2.4 best effort disaster zone. Use the 3-channel plan, or if you're very familiar with it, go to a 4-channel plan. We covered the roaming, how access points, how clients will move from one access point to another, how we can improve that, and I showed you some commands and outputs on what we can look when roaming doesn't work or when it works, so we can see how it works. So thank you very much.